In this video, we're going to talk about sample proportions. So what we've been talking about this chapter is samples of a larger population and all the different information and data values and all that good stuff that you can find of a sample that may lead you to make some conclusions about the larger population without having to survey or collect data on the entire population. So what we're going to be doing in this video is talking about all the different ways that we can describe the distribution of those samples of a larger population. So first term or phrase, I guess, is the sampling distribution of the sample proportion. So if we have p hat, right, and that is the sample proportion, how is that distributed in all samples of the same size from that same population? So for example, if you were to take a group of pennies, so n equals 20 pennies, and if you were trying to find the sample proportion of those smaller groups of pennies of a larger population of said pennies, what is the population or percentage that are from the 2000s? So, there's a date on all of our coins in the States. So what you could do is you could take many small samples of pennies and figure out what proportion of those 20, for example, are from the 2000s. And so all these little p hats here in blue are all of the samples, the SRSs that you ran or somebody ran to figure out what the sample proportion distribution of the sample proportion is. And something that we can do, and of course we are very well versed in describing how a distribution is distributed. So we could talk about shape, center, and variability of sample proportion distributions. All right, imagine for a moment that there is a large candy dispenser and it's got many different colored candies. Some are, I don't know, orange and brown and yellow. I mean, does that say Reese's Pieces to you? Because it does to me. So imagine you've got a little candy dispenser with Reese's Pieces in there. And so these graphs that you're looking at are the approximate sampling distributions of our sample proportion of orange candies for different combinations of our p-value, so that is our population proportion, and our sample size, or n. So what we're trying to do is with the, in the same vein as the pennies example, you're taking a lot of small groups of candies and figuring out what is the proportion, what is the sample proportion of orange candies, given that there are other kinds of colors of these candies in this this vessel. So, fun fact, here's some relationships, no matter if you're talking about candy or something else. So when your n, or your sample size, is small and p is close to 0, we get a distribution that is skewed to the right. So that's something like this. We got a skew to the right. Remember, it's skewed to the right or the left depending on where the tail is. So the tail here is to the right. And I'm not sure that n is 100 is a small value here, but it still looks a little skewed to the right. Now, if you still have a small n value, small sample size, but your p, or your population proportion, is close to 1, you actually get a distribution that is skewed to the left. So n is small, you get a skew. P is close to 0, you get skewed to the right. P is close to 1, you get skewed to the left. So skewed to the left here, right? N equals 25 is pretty small, at least compared to 100, but we'll give it to 100 as well. That's going to be skewed to the left. So the other thing that can happen is that we get a more normal distribution, right? Where it looks like more of a bell curve. Well, that is when P is closer to 0.5 or N is larger. So you still get a nice bell curve looking curve when N is 25 or when N is 100. So that P value being 0.5 is really important in terms of having a more normal distribution. So what else can we analyze about these orange candies? Well, we can talk about center. And so this one's a little different, but it's kind of cool, kind of nice. So the mean of the sampling distribution, p hat, is equal to the population proportion of p. So no matter what your p-value is, your p hat center, your mean or your median, is going to be the same thing. So for example, if we have 0.10 here, you can see in the graph that the measure of center is going to be at 0.10, at least close to. But look, our mean is 0.1. Same deal if p is 0.5. Our mean here, 0.5. And, well, it shouldn't shock you that if our p-value is 0.9, our mean is also 0.9. So that's the relationship of our sample proportion distributions to our center, at least, of our population proportion. They match. All right, so last up, but certainly not least, is variability. And the variability that we're going to focus on here is going to be standard deviation, so our little sigma of our p hat. So sigma, or standard deviation, has a relationship between n and p, and the relationship is as follows. So if you have a p-value that is close to 0.5, so somewhere in the middle, that standard deviation is going to be larger than if your p-value was on the ends of the spectrum, so closer to 0 or closer to 1. So if you look at our p-value here of 0.1 or a p-value here of 0.9, our standard deviations are the same. It's going to be 0.030. But if that p-value is in the middle, so at 0.5, our standard deviation actually is 0.05. So what ends up happening is for a specific value of p, so our population proportion, the standard deviation of p hat, so the standard deviation of our sample, gets smaller as n gets larger. So for example, multiplying the sample size by 4 cuts the standard deviation in half, so it has an inverse proportional relationship. So now let's sum up all the things that we just talked about in a nice little color-coded chart. So of course, we are working with a sample size of little n of a larger population of size capital N. And P, again, is our proportion of success, and that is for the population. And then, of course, P hat is our sample proportion of successes. So first up is mean, because I personally think that's the easiest part. So if you want the mean or the average of your sampling distribution of P hat, all you got to do is match it with just regular old P, or the proportion of successes in the population. Easy peasy. Next up, standard deviation. How do you calculate that? Well, you take P, the same p-value as this, and you multiply it by 1 minus your P, and you divide it by n of your sample size, and you take the square root, and there's your standard deviation. But the caveat there is, this works as long as the 10% condition is satisfied, where your sample size is less than 10% of your entire population, or your capital N. So that would mean, if that is satisfied, that your standard deviation of your sample proportion measures the typical distance that that p hat is from the actual p value. So a little different than how we've defined standard deviation in the past. Another thing to note about standard deviation in terms of sample proportions is that it assumes that all the observations are independent. So if it's not independent, that standard deviation isn't going to work, as well as if the sample size is too large, so greater than 10% of the actual population, our calculated value of our standard deviation will also be too large. So keep in mind about independence and our 10% condition there. And then last up, our sampling distribution of p hat is approximately normal, so its shape is approximately normal, as long as the large counts condition is satisfied. So that means that our sample size times our p-value of our population proportion is multiplied together greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. So that large counts condition must be met in order to assume that anything is approximately normal, because obviously if we assume things are approximately normal and they're not, any decision that we make based on that assumption is gonna be wrong, and we don't like that. So let's do one last example and we'll call it a day. So this one is called backing the pack. So our problem says that suppose that 84% of students at a large high school regularly use a backpack to carry their books from class to class. Imagine taking an SRS of 100 students and calculating our p hat, or our sample proportion, which means that the proportion of students in the sample who regularly use a backpack. So first up, let's identify the mean of the sampling distribution of p hat. So as we know, our mean of our sampling distribution of p hat is the same as our population proportion, and that is 84%, or 0.84. Like I said, easy peasy. All right, next up, let's calculate and interpret the standard deviation of the sampling distribution of p hat. And then, of course, let's verify that the 10% condition is met, because we can't use it without that. All right, so the first thing that I'm going to say about this is I'm going to try to meet that 10% condition first, because it's going to impact the standard deviation that I can find. So Remember that the 10% condition is our sample size n has to be less than 10% of the entire population, or a capital N. So if our little n is 100, we can calculate the minimum number of students, or the population, that this must have in order for the rest of this problem to work. So that must mean that our entire high school population in this scenario has to have over 1,000 students. So if that is true, we can calculate the standard deviation as such. So the standard deviation of our sampling distribution p hat is this p times 1 minus p over n. We plug in those values and we get 0.0367. Now, that's a lovely number, but what does that mean? So that means that the sample proportion of students who regularly use a backpack will typically vary by that number, 0.0367, from the true proportion of p equals 0.84. So, last but not least, let's describe the shape of the sampling distribution of p hat. And of course, we're going to justify our answer. So for this one, I'm going to start with the large counts principle, or principles, where we have our n times p has to be greater than or equal to 10, and our n times 1 minus p also has to be greater than or equal to 10. So n times p in this scenario gives me 84, which is certainly greater than or equal to 10, and also our n times 1 minus p is 16, which is less great, but still greater than 10. So both conditions are met, and that means that the sampling distribution of our p hat is going to be approximately normal. So it gives us a nice bell curve shape. And all of the things that have to do with being approximately normal will apply, which is great. What's also great is that this video is over. Thanks for watching.